You fire an electron at two slits. It passes through both, hits a screen, builds an interference pattern like a wave. Now you watch which slit it uses. The pattern vanishes. Two bands. Particle behavior. The electron knew you were watching. That is not a metaphor. That is 1801 to 2025 laboratory results repeated in Vienna, Bologna, Tübingen, across satellites orbiting Earth. This is not philosophy. This is measurement. And measurement does not care what you believe. The strangeness sits in plain view. You learned in school that things are either waves or particles. Water makes waves, rocks are particles. Light seemed like waves because it bent around corners, created fringes, interfered with itself. Then 1805. Thomas Young stood in front of the Royal Society in London with a paper titled On the Theory of Light and Colors and showed them sunlight passing through two pinholes onto a screen. Bands of light and dark, interference, waves overlapping, canceling, amplifying. Isaac Newton had said light was particles, little bullets flying through space. Newton's reputation was massive. His corpuscular theory dominated for a century. Young's demonstration killed it. Young knew what he was seeing. When two water waves meet, they add up or cancel out depending on whether their peaks align. Light did the same thing. The bright bands appeared where light waves from both slits arrived in phase, crests meeting crests. Dark bands formed where one wave's crest met the other's trough. Wave interference. The mathematics worked. The predictions matched. By 1820, most physicists accepted that light was a wave traveling through some invisible medium they called the ether. Clean answer, neat theory, dead wrong in one critical way. 1899, Max Planck tried to explain why hot objects glow the colors they do. Classical wave theory predicted infinite energy at short wavelengths, the ultraviolet catastrophe. His solution required light to come in discrete packets, quanta, with energy proportional to frequency. Einstein pushed further in 1905 with the photoelectric effect, showing light knocked electrons out of metal in a way that only made sense if light arrived as particles, photons, each carrying a specific energy. 2 Nobel Prizes later, everyone agreed light was particles again. Except Young's experiment still sat there showing waves. Wave-particle duality. Uncomfortable phrase. Physicists hated it. Niels Bohr developed complementarity in 1927, the Copenhagen interpretation, arguing that light was neither wave nor particle until you measured it. Then it became whichever one the experiment asked for. The act of measurement determined reality. That claim sounded insane but matched every experiment. Werner Heisenberg formalized it with his uncertainty principle the same year. Position and momentum, wave properties and particle properties, you could not measure both precisely at once. And Louis de Broglie suggested in 1923 that if light waves could act like particles, maybe particles could act like waves. Every particle has a wavelength equal to Planck's constant divided by its momentum. Electrons should interfere like light. If you value documented quantum mechanics history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Nature Volume 401, published October 14th, 1999, reporting Marcus Arndt and Anton Zeilinger's University of Vienna buckyball interference observations, and the American Journal of Physics, Volume 71, Number 4, from April 2003, detailing fullerene molecule quantum behavior, verified at MIT gratings, fabricated by Professor Henry Smith and Dr. Tim Savas. Now back to the information. Clinton Davison and Lester Germer in 1927 at Bell Labs fired electrons at a nickel crystal and saw diffraction patterns. George Paget Thomson, son of J. Thomson, who discovered the electron, independently showed the same thing that year at the University of Aberdeen. Electrons were waves. The Nobel Committee gave them the prize in 1937. J. got his for proving electrons were particles. His son got his for proving they were waves. Both were correct. Both were incomplete. The real question waited in a thought experiment nobody could build. What happens if you send electrons one at a time through 2 slits? Does each electron interfere with itself? 1961. Klaus Jonsson at the University of Tübingen in Germany machined slits 300 nanometers wide into copper foil using an electron microscope. He fired a 40 kilo-electron-volt electron beam through the slits. Interference fringes appeared on the photographic plate. First direct proof that electrons diffract through actual double slits like Young's light experiment. Jonsson even demonstrated interference with 5 slits. The patterns matched de Broglie wavelength calculations exactly. But the electron beam contained millions of electrons at once. Maybe they interfered with each other, not with themselves. 1974, Pier Giorgio Merli, Gianfranco Misiroli and Giulio Pozzi at the University of Bologna ran the experiment with individual electrons. They used an electron biprism, not slits, but functionally equivalent. The key was detecting single electrons one at a time, with long enough gaps between them that only one electron existed in the apparatus at any moment. They watched the interference pattern build up spot by spot on the detector screen. Each electron contributed one dot to the pattern. After enough electrons, thousands of them, the full interference emerged. Each electron passed through both paths and interfered with itself. 2002, Physics World readers voted it the most beautiful experiment in physics. 1989. Akira Tanomura and colleagues at Hitachi Advanced Research Laboratory pushed even further with electron field emission sources and positioned sensitive electron counting systems. They filmed the buildup process in real time. The electron source had to remain stable for over 20 minutes while the pattern accumulated one electron at a time. If the apparatus drifted even slightly, the interference would blur. It did not drift. The fringes appeared exactly as quantum mechanics predicted. The footage exists. You can see quantum behavior happening live, particle by particle, probability becoming pattern, but electrons are small. Maybe quantum strangeness only applies to tiny things, fundamental particles. Scale it up, 1991. Oven Carnell and Jürgen Lineck sent metastable helium atoms through micrometer scale slits in gold foil. Atoms are composite objects. Protons and neutrons and electrons bound together. Still showed interference. 1999, the big one, Marcus Arndt, Anton Zeilinger, and the Vienna Quantum Optics Group demonstrated interference with buckyballs, carbon-60 molecules, 60 carbon atoms arranged in a soccer ball structure. Each molecule has a diameter of about 1 nanometer, 7/10 exactly, mass of 720 atomic mass units, 350 times larger than their de Broglie wavelength. The Vienna setup heated fullerene powder in a ceramic oven to 900 Kelvin, sublimating it. Molecules emerged one by one through a small slit, traveling at about 200 meters per second with a thermal velocity spread of 60%. They passed through a silicon nitride diffraction, grading with slits 50 nanometers wide, spaced 100 nanometers apart. Thickness only 200 nanometers along the beam direction. Detection happened by ionizing the molecules with a laser and counting the ions. Interference pattern, each buckyball containing 430 internal degrees of freedom, accounting for all possible vibrations and rotations, still behaved as a coherent quantum wave. Published in Nature, Volume 401, page 680 on October 14, 1999. 2012. Stefano Fraboni and colleagues in Italy performed the first actual double-slit experiment with electrons and real nanofabricated slits following Richard Feynman's original thought experiment scheme. 100 nanometer wide slits, single electron detector. Pattern buildup observed one electron at a time. Each electron decided its landing position according to quantum probability distributions that required the electron to sense both slits simultaneously, even though it was detected as a localized particle. 2013. Quantum interference demonstrated with molecules containing 810 atoms, total mass over 10,000 atomic mass units. The experiment reached its published limit around molecules with 2,000 atoms and 25,000 Dalton's mass. Now the uncomfortable part. Put a detector at the slits. Watch which path the particle takes. The interference pattern dies completely. You get two strips on the screen, classical particle behavior, as if the particle traveled through one slit or the other, but never both. This is not subtle. The fringes vanish. Bright and dark bands smooth into two overlapping Gaussian distributions. The particle stops acting like a wave the moment you acquire information about its path. The moment you can answer the question, which slit did it go through? Quantum behavior collapses into classical behavior. Feynman proposed this as a thought experiment in 1965 in Volume 3 of the Feynman Lectures on Physics. He wrote it as an impossibility because detectors at that scale would obviously disturb the particle, except that misses the point. The detector does disturb the particle, but not in a classical sense. It does not need to bounce photons off the electron or mechanically deflect it. The disturbance is informational. The detector becomes entangled with the particle's quantum state. That entanglement destroys coherence between the two paths. Decoherence. The particle's wave function does not collapse in some mystical way. It spreads into the environment. The interference requires phase coherence between paths. Gaining which path information guarantees loss of coherence. Practical demonstration. Cover one slit with a polarizing filter oriented vertically. Cover the other slit with a horizontal polarizing filter. Fire photons through. The interference pattern vanishes even though you're not actually measuring anything. The polarization acts as a witch path marker. A photon polarized vertically must have come through the first slit. A photon polarized horizontally came through the second. The information exists in principle whether you measure it or not. That possibility alone kills the interference. Now add a third polarizer at 45 degrees just before the detector. The witch path information gets erased. Every photon reaching the detector is polarized at 45 degrees. You can no longer determine which slit it used. The interference pattern returns. Quantum eraser. If you value documented particle physics and interference research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from the Zeitschrift für Physik, Volume 161, page 454, published 1961, documenting Klaus Jönsson's electron double-slit work at Tübingen University. And Physical Review, a Volume 65 from 2002, reporting double-slit quantum eraser studies by Walborn and colleagues at Universidade Federal de Rio de Janeiro with full experimental verification. Now back to the information. 1978. John Archibald Wheeler conceived the delayed choice experiment. The idea pushes causality. Set up a Mach-Zehnder interferometer, essentially a double-slit equivalent using beam splitters and mirrors. Send a photon in before it exits. Choose randomly whether to measure which path it took or to measure interference. The choice happens after the photon already passed through the beam splitter where it should have decided to be a particle or a wave. Wheeler imagined this on cosmic scales. A photon from a distant quasar gets gravitationally lensed by a galaxy between the quasar and Earth. The photon arrives via two distinct paths around the galaxy, billions of years of travel. At the last moment, you choose whether to detect which path or to measure interference. Does your present choice retroactively determine what the photon did billions of years ago? No, not retrocausality. Superposition? The photon never made a choice at the galaxy. It traveled in a quantum superposition of both paths. Only when you measure does a definite outcome appear. Delayed choice does not change the past. It reveals that the past was never as definite as classical intuition suggests. Wheeler's thought experiment got realized in 2007 by Vincent Jacques, Alain Aspect, and colleagues in France using single photons and an electro-optic modulator as a high-speed random choice device. The photon's behavior at the detector depended on the measurement choice made after it passed through the interferometer. No paradox. Pure quantum mechanics. 2017. Francesco Vedavato and collaborators extended Wheeler's delayed choice to space using the Matera Laser Ranging Observatory in Italy and a satellite in low Earth orbit. Photons reflected off retro-reflecting mirrors on the satellite traveling at high speed. The choice between particle measurement and wave measurement happened at the ground station while photons were propagating down from the satellite over thousands of kilometers. Quantum behavior confirmed at unprecedented scales. Published in Science Advances, Volume 3 on October 20th, 2017, the quantum world does not care about distance or about what seems reasonable. Quantum eraser experiments. Marlon Scully and Kai Druhl proposed it in 1982 in Physical Review, a Volume 25. Generate entangled photon pairs using spontaneous parametric down conversion. Send one photon through a double slit. Its entangled partner carries which path information. Measure the partner photon in a way that erases the information. Interference returns. Measure it to reveal the path. Interference stays gone. The twist is timing. You can make the measurement on the partner photon after the first photon already hit the detector. The interference pattern only appears when you sort the detected photons based on how their partners were measured. No signal travels faster than light. No retrocausality. Just quantum correlations that violate every classical expectation. Yoon-Ho Kim and colleagues performed the full delayed choice quantum eraser in 1999 at the University of Maryland, Baltimore County. They used a beta barium borate crystal to create entangled photon pairs. One photon, the signal photon, went toward detectors. Its partner, the idler photon, went through a series of beam splitters and mirrors that either preserved or erased which path information. The signal photons hit detector D0. By themselves, they showed no interference pattern, just a broad distribution. But separate the data based on which idler detector clicked. Detectors D1 and D2 preserved which path information. Detectors D3 and D4 erased it. Plot only the signal photons whose idlers hit D3. Interference pattern. Plot those whose idlers hit D4. Different interference pattern shifted in phase. Plot those whose idlers hit D1 or D2. No interference. The choice of measurement on the idler photon, made after the signal photon already hit D0, determined whether interference appeared in the subset. This is not time travel. This is not consciousness collapsing wave functions. This is selective data analysis, revealing quantum correlations. The total pattern at D0 always looks like no interference because the different subsets add up to wash out the fringes. You need the coincidence counting between signal and idler detections to extract the interference. Critics argue the experiment proves nothing strange. Proponents argue it demonstrates non-local quantum correlations in time. Both agree the math works and the experiments repeat consistently. Published results keep confirming it. 2014, Peng and colleagues demonstrated delayed choice quantum eraser with thermal light in Physical Review Letters, Volume 112, 2023. Observations confirmed with coherent photons published in Scientific Reports, Volume 13. The observer effect does not require consciousness. Place a detector, any detector, a photon counter, a polarizing filter, a scattering medium that distinguishes particle paths. The interference pattern collapses, not because someone is watching, because a measurement apparatus extracted information from the quantum system and got entangled with it. The electron or photon couples to the detector's internal degrees of freedom. The combined system enters a state where different measurement outcomes correspond to orthogonal quantum states that cannot interfere. Decoherence explains it without invoking consciousness or special observer status. 1987. Partial witch path information experiments by teams including Gregor Wise and Anton Zeilinger showed you can trade visibility for distinguishability gradually. Acquire a little witch path information, the interference fringes fade slightly. Acquire more information, they fade more. Acquire complete information, they vanish. The relationship is quantitative, described by inequalities relating fringe visibility to the quantum state, distinguishability of the paths, quantitative wave-particle duality, 2011, Stefano Fraboni, Giancarlo Gazzati, and Giulio Pozzi at the University of Modena and CNR Institute of Nanoscience demonstrated a witch-way detector using transmission electron microscopy. They covered one slit with a filter made of low atomic number material. Electrons passing through the filtered slit underwent inelastic scattering and emerged as spherical waves with no definite phase relationship. Electrons passing through the unfiltered slit underwent elastic scattering and emerged as cylindrical waves. Two different wave types cannot interfere, even though both slits stayed open. The filter acted as a localization mechanism. The electron's wave function collapsed at the covered slit because of the inelastic interaction. The interference pattern disappeared. Published in Physical Review Letters, Volume 107. Does the wave function collapse? Depends on interpretation. Copenhagen interpretation says yes, instantly, triggered by measurement. Many worlds interpretation says no, never. The universe splits into branches. de Broglie-Bohm pilot wave theory says there is no wave function in physical space, just particles with definite positions guided by a pilot wave. Cubism says the wave function represents an observer's subjective knowledge, and collapse is just a Bayesian update. Relational quantum mechanics says wave functions are observer-dependent and collapse happens relative to reference frames. All interpretations make identical experimental predictions for every test we can currently perform. The math works the same. The philosophical implications diverge wildly. Experiments to distinguish interpretations face fundamental obstacles. Many worlds predicts nothing different from Copenhagen for any measurement you can make within a single branch. De Broglie-Bohm reproduces standard quantum predictions, exactly in its statistical limit. Cubism argues experiments cannot decide because the question is about epistemic states, not ontology. We built quantum computers. They work. We use quantum cryptography. It is secure. We perform quantum teleportation routinely. None of this tells us which interpretation is correct, because all interpretations predict the same outcomes for these applications. Recent proposals target the measurement problem more directly. Objective collapse models, like the Gherardi-Rimini-Weber theory, propose spontaneous wave function collapse with a frequency proportional to particle number. Large objects collapse quickly. Small systems rarely collapse. This predicts deviations from standard quantum mechanics that experiments could test. 2021 experiments constrained collapse parameters, but have not ruled out the models entirely. Gravitationally induced collapse theories link wave function, reduction to space-time curvature. Roger Penrose suggested this in the 80s. Testing requires quantum superpositions of objects massive enough that gravitational effects matter. Current experiments with microspheres approach the regime. Published results in Nature and Physical Review Letters keep pushing the mass limits upward. The strangeness scales. You have probably heard consciousness causes collapse. Wrong. Origin is Eugene Wigner in 1961 discussing his friend paradox. Wigner argued that if measurement requires consciousness, then his friend measuring a quantum system inside a closed lab causes collapse for the friend. but Wigner outside sees the entire lab in superposition until he opens it. Wigner presented this as a reductio ad absurdum, showing something was wrong with consciousness-based interpretations. Later interpretations misread it as support for consciousness collapse. Experiments decisively show consciousness is irrelevant. Detectors record quantum measurements with no conscious observer present. The measurements still destroy interference. Published data from automated quantum experiments running for hours with nobody watching confirms this repeatedly. 2012. Hitachi developed position-sensitive electron counting systems stable enough to watch interference patterns form over 20-minute integration times with single electron sources weak enough that electrons arrive separated by milliseconds. No electrons overlapping in the apparatus. Pattern still forms. Each electron interferes only with itself. The detector clicks at specific positions. The pattern emerges from probability distributions calculated from the Schrödinger equation. For the electron wave function passing through two slits with appropriate boundary conditions. The de Broglie wavelength for 40 kilo electron volt electrons is about 6 picometers. The slits are 100 nanometers wide. Diffraction theory predicts the observed patterns to within measurement error. Quantum tunneling shows up in the experiment too. Electrons occasionally appear in regions that classical mechanics forbids. The wave function has non-zero amplitude in classically forbidden zones. Low probability, but non-zero. Detectors placed in those regions click occasionally. The rate matches quantum predictions. Place detectors everywhere. Map out the full probability distribution. It matches the square of the wave function calculated from the Schrödinger equation. Quantum mechanics is not failing. It is not incomplete. It is not hiding variables. Every test agrees with standard quantum theory. Hidden variable theories tried to save determinism. Einstein wanted them. He hated the Copenhagen interpretation. God does not play dice. He argued quantum mechanics was incomplete, missing hidden variables that determined outcomes. 1935. The EPR paper, Einstein, Podolsky. Rosen claimed quantum mechanics allowed entangled particles to show correlations that violated local realism. Either quantum mechanics was wrong or nature was non-local. John Stuart Bell proved in 1964 that local hidden variable theories cannot reproduce quantum predictions. Bell's inequality provides a testable bound. Quantum mechanics violates it. Experiments must decide. 1972. Stuart Friedman and John Clauser at Berkeley measured polarization correlations of entangled photons. Violated Bell's inequality. 1982. Alain Aspect in Paris closed the timing loophole using fast switches. Violated Bell's inequality. 2015. 3 experiments simultaneously closed all major loopholes. Delft, Vienna, Boulder. Violated Bell's inequality. 2022. Anton Zeilinger, John Clauser. And Alain Aspect won the Nobel Prize in Physics for experimental tests of Bell inequalities and pioneering quantum information science. Nature is non-local. Measurement outcomes on entangled particles are correlated in ways no local hidden variable theory can explain. The universe is fundamentally quantum, but the double-slit experiment holds the center. It shows superposition, interference, complementarity, measurement, backaction, decoherence. Feynman was right. All of quantum mechanics is in there. Think through the implications carefully enough, and you understand everything strange about the quantum world. Single particles interfering with themselves means the particle does not have a definite path. Watching the particle collapses, the superposition means information and entanglement matter more than classical notions of disturbance. The pattern building up particle by particle means probability is fundamental, not ignorance. 2019. Experiments confirmed quantum behavior in molecules with 430 atoms and 6,910 atomic mass units using tetraphenylporphyrin derivatives. TPPF 152, formula C 168 OH 94F 152 O8N4S 4. Mass 5,310 AMU. Interference fringes appeared in a Kapitsa-Dirac-Talbot-Lau near-field interferometer using 3 gratings and a standing light wave. These molecules are large enough to see in electron microscopes. They contain over 1,000 internal degrees of freedom. Room temperature, thermal energy constantly excites vibrations and rotations, still coherent, still quantum. Published in Nature Communications, Volume 2, Article Number 263. The current limit is not fundamental. It is technological. Larger molecules require lower temperatures to maintain coherence long enough. Vibration and rotation couple the molecule to the environment through thermal photon emission. Each emitted photon carries which molecule information? Decoherence. Cool the molecules below vibrational excitation energy, and the emission stops. Isolate them from gas molecules and blackbody radiation, Interference can work. Experiments are pushing toward viruses, toward bacteria, toward objects you can see with optical microscopes. No fundamental limit stops it. Practical challenges grow severe. Nobody thinks quantum mechanics will fail. The theory has survived every experimental test for over a century. You do not need exotic interpretations to explain the double-slit experiment. The math is standard first-year quantum mechanics. Wave function for a free particle with momentum p passing through a barrier with two slits of width ww separated by distance d. Solve the Schrödinger equation with appropriate boundary conditions. The wave function after the slits is a sum of two terms, one from each slit, each diffracted according to Huygens' principle. At a screen distance L behind the slits, the interference appears with fringe spacing proportional to wavelength lambda times L divided by d. Brightness at each point is proportional to the square of the wave function amplitude. Integrate over all possible wavelengths for real sources with velocity distributions. The math works. The predictions match. Every time. Detectors at the slits add entanglement terms to the Hamiltonian. The particle wave function couples to detector internal states. The combined wave function becomes a sum of product states, each product pairing a particle path with a detector outcome. The different detector outcomes are orthogonal quantum states. Interference requires adding amplitudes for different paths that lead to the same final state. When detector states differ, the final states differ. Orthogonal states do not interfere. The fringes wash out, even though no classical force disturbed the particle. Pure quantum mechanics. No consciousness, no philosophy, just unitary evolution under the Schrödinger equation, plus measurement postulate or your preferred interpretations equivalent. The philosophical weight comes from accepting what the math says. Classical physics assumes definite properties exist, independent of measurement. Quantum mechanics says no. Properties have probability, amplitudes that obey linear superposition. Measurement collapses superposition to eigenstates, or entangles the system with a measurement apparatus, or splits the universe into branches, depending on interpretation. All interpretations agree on the experimental predictions. All interpretations agree the particle does not have a definite position until measured. All interpretations agree watching the particle changes the outcome in the double-slit experiment. The disagreement is metaphysics. Science does not settle metaphysics. Science settles predictions. Quantum mechanics predicts the double-slit results exactly. Always. No failures. Not once. Build the experiment with photons, electrons, neutrons, atoms, molecules. Change the slit width, the slit spacing, the screen distance, the particle energy. Add detectors, remove detectors, polarize the paths, erase the markers. The predictions match the results, every single time. Physics has no deeper confirmed theory. General relativity describes gravity but fails at quantum scales. Quantum field theory describes particles but ignores gravity. Quantum mechanics is the foundation underneath all of it. 2025, experiments continue. Groups are attempting double-slit interference with nanoscale diamonds, with microspheres, with levitated particles. The technology improves, the isolation chambers get better, the decoherence times extend, the mass limits climb. Eventually, someone will interfere a macroscopic object and watch the pattern build. Nothing in the laws of physics prevents it. Only engineering. The wave functions are there. The superposition states exist. Quantum mechanics does not turn off at large scales. It gets harder to isolate from the environment. Decoherence grows with system size, but it is not a fundamental barrier. What happens when we succeed? When we interfere an object you can hold in your hand? Interpretations predict different things. Copenhagen says the wave function collapses anyway when it interacts with a classical detector. Many worlds says the universe splits. Objective collapse says the object triggers spontaneous localization. We will test it. We will measure it. We will compare predictions to results. So far, over a century of tests, quantum mechanics has not failed. Not once. The double-slit experiment stands at the center, showing us that reality at its foundation is probabilistic, non-local, contextual, and stranger than any story humans invented before the 20th century. September 2002, Physics World Survey. Most beautiful experiment in physics. Number 1, the double-slit experiment with single electrons. Number 2, Galileo's experiment on falling bodies. Number 3, Millikan's oil drop experiment. Number 4, Newton's decomposition of sunlight with a prism. Number 5, Young's double-slit experiment with light. The double-slit appears twice in the top 5. Once as the original light experiment that proved wave theory in 1801, once as the single electron version that proved wave-particle duality in 1974. The experiment defines quantum mechanics. It is the heart of the mystery. Everything else follows from understanding this one setup. 2 slits, one particle at a time. Interference pattern builds. Watch the particle. Pattern vanishes. That is quantum mechanics. That is the universe. Here's the disturbing part nobody tells you clearly. The experiment does not just show that particles are sometimes waves, it shows that reality is contextual. The particle's properties depend on the measurement context. Not just unknown until measured, actually undefined until measured. The wave function is the complete description. There are no hidden variables underneath determining outcomes. Bell's theorem plus decades of experiments proved that conclusively. The wave function evolves deterministically according to the Schrödinger equation until measurement. Then outcomes appear randomly with probabilities given by the Born rule. That randomness is fundamental, not ignorance. Not chaos, not hidden complexity. Fundamental indeterminacy built into the structure of the universe. Or, if you prefer many worlds, the outcomes are not random. All outcomes happen. The universe splits into branches. Each branch sees one outcome. The branching is deterministic. The Born rule emerges from the measure on branches. No true randomness, just apparent randomness, because you only experience one branch and cannot predict which. Same experimental predictions, different metaphysics. We cannot currently test which interpretation is correct. Maybe we never will. Maybe the question is meaningless, because both interpretations are mathematical reformulations of the same underlying quantum formalism that makes identical predictions for all measurements, but the strangeness remains regardless of interpretation. Send an electron through two slits. It interferes with itself. That is a fact, not interpretation dependent, not philosophical. The interference pattern appears. The fringes have specific positions and specific intensities matching quantum calculations. Watch which slit it uses. The pattern vanishes. Also a fact. The loss of interference matches quantum predictions exactly when you include the detector in the quantum state and calculate the full entangled wave function. The electron plus detector cannot show interference because the detector states corresponding to different electron paths are orthogonal. Math, physics, experiments, all consistent. The scale continues to puzzle. Why do we not see macroscopic objects in superposition? Why does a baseball have a definite position? Why does the moon exist when nobody looks? Decoherence answers most of it. Large objects have huge numbers of particles interacting with huge numbers of environmental photons and air molecules in heat bath modes. Each interaction entangles the object with the environment slightly. The coherence decays exponentially. For a dust particle in air at room temperature, decoherence time is less than a nanosecond. For a baseball, immeasurably shorter. Quantum superposition decays into classical probability distributions before you can measure it. The math works out. Experiments on ever larger molecules confirm the decoherence mechanism. It is not a new law, just the Schrödinger equation applied to large systems coupled to environments. But decoherence does not solve the measurement problem completely. It explains why we do not see superpositions persist. It does not explain why we see single outcomes rather than experiencing superposition directly. Copenhagen adds collapse. Many worlds adds branching. Objective collapse adds new physics. The debate continues. The experiments continue. The double-slit sits at the center, demanding we accept that particles are not little balls with definite positions and momenta traveling on definite paths. They are quantum objects described by wave functions that evolve unitarily and exhibit interference when multiple amplitudes contribute to the same outcome. 2024. Anton Zeilinger interviewed after receiving the Nobel Prize. Reporter asked about the interpretation debate. Zeilinger replied that quantum mechanics is about information. Measurement extracts information from quantum systems. The information you can extract is limited by the uncertainty principle. The act of extracting information changes the system's quantum state. That is not a disturbance in the classical sense. It is a consequence of information and state being the same thing in quantum mechanics. Know the state, you can predict measurement probabilities. Measure something, the state updates. The double-slit demonstrates this with perfect clarity. Interference proves the particle is in superposition of both paths. Measurement proves the particle went through one path. Both are true, not contradictory, contextual, but maybe the most shocking aspect is how simple the experiment is conceptually. Two holes, one particle. Interference appears. Watch it. Interference disappears. You can explain it to a child. You can build a version at home with lasers and polarizers. Yet nobody fully understands it. Not in the sense of matching intuition to the mathematics. The math works. The predictions match. The intuition fails. Particles are not waves. Particles are not classical bullets. Particles are quantum objects. And quantum objects do not obey the rules you learned from everyday experience. Your intuition is trained on classical physics. Quantum mechanics is not classical. Your brain cannot picture it correctly because it did not evolve to handle superposition and entanglement. Accept the math, trust the experiments, stop demanding classical pictures. Here is a documented detail from the 2012 Froboni experiment published in Applied Physics Letters, Volume 101. They fabricated the slits using focused ion beam milling in silicon nitride membranes. Slit width 83 nanometers. Slit separation 270 nanometers. Membrane thickness 100 nanometers. They used a transmission electron microscope operated at 200 kiloelectron volts. Single electrons were detected using a cooled CCD camera with single electron sensitivity. Integration time per frame was 10 seconds. Total recording time 20 minutes. Each frame recorded approximately 10 electrons. The interference fringes appeared clearly in the accumulated data with visibility around 30%. The visibility limitation came from chromatic aberration in the electron source and mechanical vibrations. Perfect coherence would give 100% visibility. 30% is excellent for this setup. The experiment conclusively demonstrated single electron double-slit interference with real nanofabricated slits, completing the vision Feynman described in 1965 when he said it would be impossible to perform. Nothing about quantum mechanics is mystical. Nothing requires consciousness. Nothing involves Eastern philosophy or holistic thinking or quantum healing or any of the nonsense that popular culture attaches to the word quantum. The universe is quantum. The math is precise. The experiments repeat. The predictions match. It is strange. It violates classical intuition. That strangeness is real. Accept it. The alternative is denying experimental results that have been confirmed millions of times by thousands of research groups across 70 years. The double-slit experiment is a probe into the foundation of reality. It shows that reality is not made of definite objects with definite properties existing in definite states. Reality is made of quantum states that encode probability, amplitudes for measurement outcomes. Perform a measurement, and an outcome appears. The probabilities are calculable from the state. The outcomes are fundamentally random, or equivalently all outcomes happen in different branches. Either way, the classical picture is wrong. There is no escaping it. The electron does not have a position until you measure it. It has a wave function that spreads through both slits and interferes with itself. The interference is not metaphorical. It is mathematical. It is physical. The bright and dark fringes have specific locations determined by the wavelength and the slit geometry. The predictions match the observations to arbitrary precision, limited only by experimental systematics. In 1999 at the University of Vienna, buckyballs containing 60 carbon atoms each, diameter about 1 nanometer, mass 720 atomic mass units, were sublimated from solid powder heated to 900 Kelvin, emitted one at a time through a collimation system, passed through silicon nitride gratings with 55 nanometer slit openings on a 100 nanometer period, and detected by laser ionization followed by ion counting. The resulting interference pattern matched quantum diffraction theory, including corrections for van der Waals interactions between the molecules and the grating walls. The molecules were large enough to see in electron microscopes. They contained hundreds of atoms. They had complex internal structure with vibrational modes and rotational degrees of freedom. They were thermal, not ground state, carrying significant internal energy. None of that prevented quantum interference. The molecular wave function remained coherent across the grating spacing. Each molecule interfered with itself. Published October 14, 1999 in Nature, Volume 4, 01 pages, 680 to 682 by Marcus Arndt, Olaf Nyers, Julian Voss-Andrea, Claudia Keller, Gerbrand van der Zau, and Anton Zeilinger from Institut für Experimentalphysik, Universität Wien, Boltzmann-Gasse 5, A1090 Wien, Austria. That paper showed that quantum mechanics applies to complex molecules under realistic conditions. The molecules interacted with blackbody radiation. They emitted and absorbed thermal photons. Each emission event carried which molecule information in principle, yet the coherence survived long enough to produce clear interference. The key was transit time. The molecules traveled fast enough that coherence lasted longer than the time to cross the grating. Later experiments with slower molecules showed reduced visibility as thermal emission increased. The theory matched. Decoherence rates scaled with temperature and internal excitation energy, exactly as quantum mechanics predicted. No surprises, no anomalies, no regime where quantum mechanics failed. Currently, the mass record stands at molecules containing thousands of atoms. The size record approaches scales visible to optical microscopes. The de Broglie wavelength shrinks to picometers, 10,000 times smaller than atomic spacing. Yet interference persists when the experimental conditions maintain coherence. Temperature must be low enough. Isolation from environment must be good enough. Transit time must be short enough. Meet those conditions, and quantum mechanics works regardless of size. No evidence for a classical quantum boundary. No evidence for consciousness-triggered collapse. No evidence for objective reduction at macroscopic scales. Just decoherence rates that grow with system complexity and environmental coupling. Quantum mechanics all the way up, as far as experiments can reach. The final twist in the knife is how ordinary this seems after enough exposure. Physicists work with quantum mechanics daily, build quantum computers, design quantum sensors, develop quantum cryptography protocols, use quantum tunneling in semiconductor devices, rely on quantum statistics for material properties, calculate atomic structure from quantum eigenvalue equations. None of it seems strange anymore. It is just physics, the math works, the devices function, the predictions match measurements. You internalize the formalism and stop asking why nature behaves this way. Nature just does. Quantum mechanics is the correct description. Classical mechanics is the approximation that emerges in the limit of large quantum numbers and rapid decoherence. The classical world is not fundamental. It is a convenient fiction that works at everyday scales because decoherence is fast and quantum effects average out. But sometimes you step back and really think about the double-slit experiment again. One electron, two paths, interference, a single particle physically passing through both slits simultaneously in some sense, except no, not physically passing through both, because if you check, it went through one or the other, but it must have gone through both to create interference. Yet checking proves it did not. Complementarity. Both descriptions are true. Both descriptions are necessary. Neither is complete. The full quantum description is the wave function. Everything else is language, trying to force quantum behavior into classical categories that do not fit. Last experimental detail worth noting comes from the 2012 Froboni group work published in New Journal of Physics, Volume 14. They demonstrated that covering one slit with a thin carbon film created inelastic scattering that destroyed interference, even though both slits remained open. The film did not block electrons. It changed their scattering type. Electrons passing through the uncovered slit scattered elastically, maintaining phase coherence, emerging as cylindrical waves. Electrons passing through the covered slit scattered inelastically off carbon atoms in the film, losing coherence, emerging as spherical waves with random phase. Cylindrical and spherical waves have no phase relationship. Cannot interfere. Pattern vanishes. The experiment showed that which-way information need not come from a traditional detector. Any interaction that localizes the electron or stamps path information onto its quantum state suffices. Published August 2, 2012 in New Journal of Physics, Volume 14, page 013010 by S. Froboni, G. C. Gazzotti, and G. Pozzi. The double-slit experiment is a century-old demonstration of quantum mechanics that has never been surpassed for clarity and strangeness. 1801. Thomas Young proved light is a wave. 1927, Davison-Germer and G. P. Thomson proved electrons are waves. 1961, Klaus Jønsson showed electron double-slit interference. 1974, Murli-Misiroli-Pozzi showed single electron buildup. 1989, Tanemura filmed it. 1999, Arndt Zeilinger did it with buckyballs. 2012, Froboni closed Feynman's thought experiment with real nanofabricated slits. 2019 experiments reached 430 atoms. Every version confirms quantum mechanics. Every version shows interference. Every version shows the pattern collapses when you watch. Every version matches the predictions exactly. You can reject the interpretations. You cannot reject the data. Interference appears when the particle's path is unknown. Interference vanishes when the particle's path is known. That is not interpretation. That is measurement. The fringes are real. The loss of fringes is real. The quantum state description works. The classical particle picture fails. Wave-particle duality is not two natures. It is quantum nature appearing wave-like or particle-like depending on what you measure. Complementarity is not mystical. It is the observation that some measurements are incompatible because their corresponding operators do not commute. Uncertainty is not ignorance. It is fundamental because position and momentum are Fourier transforms of each other. Wave functions are not just probability tools. They are the complete quantum state. There are no hidden variables. Bell proved it. Experiments confirmed it. This is settled physics. The strangeness is permanent. Quantum mechanics will never feel intuitive because human intuition is classical. Your experience is macroscopic objects with rapid decoherence. You never see superposition directly. You never experience entanglement at the personal level. Your neural circuits are classical information processors. They cannot represent quantum states. Asking for quantum intuition is asking your classical brain to become a quantum computer. It will not happen. The best you can do is learn the math, trust the experiments, and accept that reality at the quantum level operates by rules different from everyday experience. The double-slit experiment demonstrates those rules with perfect clarity. 2 slits, 1 particle, interference pattern. Watch it. Pattern vanishes. That is quantum mechanics. That is nature. That is the universe we inhabit. Strange, confirmed, irreducible.